Good morning. So my name is Joaquin van Schoren, and I will talk about OpenML, which is a platform for collaborative machine learning. Here we go. So me, like I think many people here, like to analyze and explore data. And I think it is often this kind of a solo affair. I write my own scripts, I do my own analysis, then I talk to other people, a few other people about it. But it's not really a social experience, right? So what if we can explore data collaboratively? What if we can do it on a web scale, where I can take data from anybody in the world, share my experiments with anybody in the world, and anybody can immediately give feedback on what I'm doing, can help me do my analysis in real time. Why is this important? Because data science is an ecosystem. There's many different roles that need to be performed in order to do good data science or good data-driven science, right? We have the domain scientists that are very good at defining problems and collecting the right data to solve a problem. There's also a big component of algorithm design and selection, and also a very big component of making the code work and scalable and work on lots and lots of data. But the problem is that these different groups, we try to do all of these things as good as we can, but we're not all experts in all fields. I wouldn't know how to sequence a gene, for instance, if I want to help with the medical research. And likewise, people who sequence genes and want to analyze their data, they always don't know what are the best techniques to do that. So there are these gaps in this ecosystem. First of all, domain experts, they don't always know which are the best techniques and how to use them. They don't want to always email the people who wrote those algorithms to ask for questions. So they use the algorithms they know, right? And vice versa, if I'm designing an algorithm, I don't want to bother people who are doing important medical research to give me data to test my new algorithm. And also, I don't speak the language, first of all, and second, it's hard for me to meaningfully extract the data from these big scientific databases. Which means that I typically test my algorithms on open data sets which are maybe 10 or 15 years old, right? The transfer to the literature is important, but it's kind of slow and it's opaque. It's full of jargon and implicit knowledge that you need to know to understand the paper fully. So it takes me a lot of time to do that. And it has also a little cross-domain relevance. If I test my very new algorithm on old data, this is not interesting for people who are analyzing the data that we generate today. Right? So there's a lot of unnecessary friction, which causes us to lose time, to spend lots and lots of time on reading papers, trying to collect data, talking to people, setting up collaborations, that others could do in a fraction of the time. If I want to find interesting data, somebody else can just give it to me, or just extract it from a database in a day, or maybe just a few minutes. Right? And some things can be automated altogether. This slows down and underpowers a lot of research. There's a lot of research out there that's not reproducible, that's not really wide enough to make really bold claims. It also slows down because we spend a lot of time analyzing data, collecting data and so on. It's also a problem for enterprises because they lack access to all the right expertise and the data. We do a lot of duplicate work that other people have been done thousands of times before, both within and outside the organization. And a lot of value that we get from data could have been achieved more faster and cheaper if we would have a means to collaborate more easily. We have this well-known shortage of data science expertise, which ultimately leads to the conclusion that data science needs to scale better, right? We need to collaborate frictionlessly across many people, across many fields, across many labs, so that we can easily find the necessary expertise and help from other people, so we can do our work much faster. We need to democratize data science more, so more people, more students have access to it and can start using it. And we need to automate a lot of the drudge work that really takes us a lot of time, and it's ultimately unnecessary. This has implications in the medical domain. You probably know John Ioannidis, who did this very big literature study showing that over 85% of findings in the medical research are either exaggerated or false, because not because they're typically just because they use the wrong statistical analysis by accident. A lot of it is underpowered. It's not sweeping enough to really state the claims that they want to that they put forward. And there's a lot of flexibility in designs. So it's not always easy to interpret whether what they did is actually valid. And it's hard to translate to applications. We could do it much better if we would have, and some subfields like genetic epidemiology, they work on much larger scales. They have tools for replicability. They openly share data and code. They're much better than other domains in this area. So how can we solve this problem? One way is to do network science. So maybe you know this guy. This is Tim Gowers. He's a field medalist, one of the biggest mathematicians of our days. And one day he was stuck on this really hard mathematical problem that has been unsolved for centuries, right? And he was just stuck on it. And instead of just putting it into his drawer, he said, let me just put this on my blog. He put all his ideas and partial progress on his blog and invited anybody in the world to help solve this problem. What happened in the next few days and weeks is that many tens and maybe even hundreds of people started making suggestions, running simulations, reformulating the problem, and within 40 days they actually solved this very hard problem. Actually, they solved a harder generalization of the original problem. It's just amazing to see how quickly ideas develop in this open collaboration. Another great example comes from astrophysics, astronomy, where we have the Sloan Digital Sky Survey, which is a robotic telescope that automatically scans the sky every night and periodically, automatically publishes all this data openly. So you can just go online and take any point in the sky, any wavelength, any depth in light years, and you can see what images exist in that part of the space. And thousands of papers come out every year based on this data. Where before you were an astrophysicist and you had an ID, for instance, do two black holes orbit around each other, you would have to write grant proposals, run simulations, ask for computing telescope time. Now you can just download the data, run data mining on it, and find these things happening in real life. Most interestingly, this has given rise to a lot of citizen science, because they have over 1 million users of their server, but there are only about 10,000 astronomers. So 99% of the people who use the data, who look at the data, are amateur astronomers, or people who are just interested in looking at the universe. And they made some new discoveries. For instance, there was this Dutch school teacher, Henny van Arkel, who noticed green blobs in the images. And so she asked, what are these? And many people said, it's probably just noise. But then other people say, hey, I've noticed this too. And they started on a hunting spree. They found different occurrences of these kind of galaxies. And now it's known as a new type of galaxy. It's actually called the Green Pea galaxy. And if you're keeping up, there's a next telescope coming up which will generate 15 terabytes of data every year for 10 years. So it's a huge amount of data that you can actually go to. Why does this work? It's because it's something that Michael Nielsen calls design serendipity. It's design the system so that you make discoveries accidentally on purpose, right? You either get any eyeballs on the data, so you have many bright minds looking at the data, they all have their own sagacious viewpoints, and they all contribute their ideas. And this means that new ideas get developed much more quickly. And also it's more enabling, because if I have to spend a week on doing something, I won't do it, but if it takes somebody else just a few seconds to do it, he will do it, and he will contribute in that way, right? And if you think about data as a new soil, you can have the image of many bright minds shining their light on the data and allowing these germs to grow into big ideas. But in order to do this, you need to remove friction, right? You want to contribute in seconds, not days. The knowledge must be organized, easy to find, and easy to contribute to. Communication must be easy, and importantly in science, you need to track who did what and give credit, because scientists won't actually just share their ideas if it has not been noted down somewhere. So this led to the idea of OpenML, because we have these millions of real open data sets being generated in medical research, astronomy, all kinds of fields. And we have these extensive toolboxes with hundreds of algorithms to analyze all this data. And we have massive amount of experiments that are running every day. Scripts are being written. And often we don't know where they are. We don't know what the experiments did before. This information is not organized, it's not shared, not in a consistent way. Which means we cannot learn across people or labs. I don't have a view, I don't know what other labs are doing. Even if they would want to share it. Sorry. Which means I have to start from scratch, which slows down my research and innovation in companies. Sorry. So this led to OpenML, which some people call like a GitHub of data science. It's a place where you can collaborate on analyzing data, right? So it has all data organized, right? So all experiments that you run, it's mostly about machine learning, so you can upload machine learning models to it. And all these models are connected to the data, to the exact code, the exact versions of the code, and to the people who generated those models. It's easy to use because it's integrated into machine learning platforms. If you use R or Weka or Python, with a few lines of code or a few clicks, you can automatically share all your experiments to the server and organize them online. It's easy to contribute because you don't have to do a lot. You can just upload a single data set or a single experiment. And we're working on this reward structure so it automatically tracks what people are contributing. So if you upload a data set to OpenML, what happens, it's automatically, you can just upload or you can just reference a data that's somewhere else, of course. It's versioned, and also it's analyzed, characterized, and organized online. So if you upload a data set, every data set gets its own web page where it has this kind of overview of the features. This is a classification data set, so you see all the classes, the distribution of the classes over each features. It computes all kinds of statistical properties of the data, and this is all automatic. You just upload data set, and this web page appears online, right? Which already helps you to dig into it, and other people can also easily understand the data that they're seeing. You can then create tasks, which are kind of a challenge. For instance, I want to do classification on this data set, and this is my target that I want to predict. And if you do this, OpenML will create something that's machine readable. So a tool like R can just download the tasks and has the data already in it, has the trained test splits in it, so you can just run experiments and automatically upload all the data to the server. If you do that, it creates a real-time overview. So here you see a timeline on the x-axis and performance on the y-axis, and so every dot here is a model, and the colors are different people, and you can see how all the models perform over time, and you can click on any of these models and see how they are built, and you can learn from that and then build better models. So you can see how the whole community kind of learns from each other and builds better models over time. It's a big collaboration. And it's also fun, apparently, because we do this in the machine learning courses, and students, they start tweeting about this. There was this one tweet saying, okay, here, mom, this is a proof that I'm studying on a Sunday. And actually, after deadlines, people still try to improve their algorithms. It's really fun. So that the code or the workflows that you upload or link to, you can just link to your GitHub account and say that's the data. The data's there, which we recommend. And it also has an API. It has a REST API to talk to the server, and it has APIs in Java, R, and Python. So you can upload all your data from your own custom tools if you want. For instance, in R, it's just 4 lines. You download the task, you build a model. This is just a random forest model in R. Then you run the model to the algorithm on the data, and then you upload the results. So it's just 4 lines of code. And you can mix and match this in any way you want, so you can automatically share all your code online. If you use one of those graphical tools like Weka WebMiner, there are plugins that you can use, and then new components appear. So you can say, okay, I'm this. You can put your login data there and automatically share all your results. And then all these, the way these experiments are shared is fully reproducible. So it makes sure that all the necessary information is there so that other people can reuse it. It's linked to the data, the flows, the version of the data and the flows, and the authors, so you always know who did what. And that way you can collect thousands of runs from all over the world, and they form one organized piece of knowledge. And they're also very detailed. We store our results on a per instance level. You can download the models, and you can have these you just don't get you don't just get a single number. So this is computed on the server, so you can easily compare the performances of models over different people. You can look at them in a lot of details, and you can reuse them in different ways. You have a website called OpenML.org, and there you can search for data. You can search by keyword, by properties. You can use tagging. Per task, you have this overview. So here you have all the workflows that have been built. You can see how well they do. So you can see which are the best solutions to the task. You get this timeline over time. You get people tweeting about it. That's what I wanted to show. And per flow, for instance, this is random forest. You can see how it performs over different data sets. And you can see the effect of parameters. For instance, in the colors, it is a number of trees that you use in the forest. You can see the effect on different kinds of data sets. And the runs, they are all very detailed and reproducible. We're still working on circles, so we're still in beta. We're now working on circles, so you can collaborate in a smaller group. Studies, where you can collaborate on a specific problem and link it maybe to a paper. Reputation building, and notebooks, so you can collaborate on building scripts. What this does is it changes the way we do data science, because we change the scale of collaboration. Now I can invite anybody to work with my data, or I can work on the data of many people, and I can include hundreds of people, and it's no problem because all their results, their contributions are organized online, so I can easily see what works and what doesn't. There's also a global organization, so I can see over the entire knowledge of OpenML which are the best algorithms, which is the state of the art. It's also changed the speed because I can automatically share my experiments. I don't need to spend weeks formatting the data so that other people can understand it. It's just automatically uploaded, and everybody can easily understand it because it's organized online. What we're also working on quite a bit is automation. We can build machine learning robots, bots that just wait for new data sets to appear and automatically run new algorithms on new data sets. Or we can add services like discovering similar data sets to yours, or do basic analysis so you get a simple report of what simple models will do on your data. And we can take all these experiments and learn on top of all these experiments to find the best way to select and optimize algorithms. We have a growing community all over the world. And to come back at healthcare, this is an area where OpenML is really helpful because this is typically a case where we have complex data and many sources of data that needs to be interconnected, right? So you need collaboration from many different people to solve these problems. We need novel machine learning methods because of these big problems like high-dimensional data. How do you analyze it? Or massively missing data. What if 50% of your data is missing? How do you handle that problem? And this requires large-scale fast collaboration. So OpenML can help here by enabling these large-scale collaborations, by ensuring reproducibility, by making data easily available, and by showing what works and what doesn't. So if I'm working on a problem, I can just see what are other people doing and how well does this work, and maybe I can apply it in my case. So we've done this for drug discovery. Maybe you know Campbell. Campbell is a big database of over 1.4 compounds. So these are possible drugs. And their activity on enzymes. So do they inhibit an enzyme? And if you inhibit the enzyme, you can also inhibit the virus or the parasite, whatever you try to target. So what we did, we extracted over 10,000 data sets from this database. We take the drugs, and then we describe their properties with fingerprinting and molecular properties. So we end up with these 10,000 regression data sets. We add them to OpenML. And the first thing we did is, of course, to run different algorithms on it. So we ran all the major machine learning models in R on it, so we can see which is the best algorithm. Turns out in this case, random forest with this particular fingerprinting is the best model in most cases. But we can also try more interesting techniques. For instance, here we used stacked generalization, which means is we take the predictions of different models and we add them to the original data, and we build a model on top of that. And that model actually is, widely outperforms all the other ones. So this model which is trained on all these 10,000 data sets and these different models, can actually give you a very good indication whether a drug is useful for a specific disease. You can also do things like multi-target learning, because in many cases you don't have a lot of data on specific targets, on specific enzymes. But what you can do, because these enzymes are related to each other, you can combine the data for enzymes that are related to each other, right? That belong to the same family or that have similar gene sequences, right? And then you can build a bigger data set, learn on top of that, and what you can see in the blue bar is that this multitask learning vastly outperforms the standard learning where you just build a single random forest algorithm. And this is just a service that you can do many more things with this. The data will be on OpenML available, so you can play with the data. And making this data publicly available to the machine learning community will, I think, automatically mean that many people will use it, will find new models which will be useful for drug research. That's it. If you want to join OpenML, we're an open community which thrives on contributions from many different people. It's a big community. We do regular workshops. We have a next workshop coming up in Low-End Center. If you're interested in joining us. And that's it. And if you have any more questions, I'll be happy to answer them. Thank you.
Thank you very much, Joachim. I haven't seen any questions on Twitter yet, so maybe there's a question from the audience here.
Yes? Okay. Cool.
The lady here.
I was wondering, is this a research tool, or are you intending to make this commercially available or something like that?
Right now it's just a research tool. Yeah. Maybe in the future it can be something else, but right now it's just a research tool. Yeah. Yeah.
Thanks for the nice talk. I understand the spirit of OpenML for fundamental research, but for a healthcare company which has a lot of private data or customer data, have you thought about it, how OpenML is useful?
There are different ways. Actually, we work with medical companies also. So I think in one case, we need to make more data publicly available, to get people's consent to make the data available for basic research. On the second hand, you can deploy OpenML within a company. Right? It doesn't make sense for a very small company, but if you're a big medical company and you can organize all this information that's within the company and maybe import data that's out there from the scientific community, that will also help you. Within hospitals, you could deploy it within hospitals. And then we need to think about, we are thinking about this, a way to share metadata, minimum amount of metadata, so you can at least figure out what are our people doing, what works, who is doing this, can I come to this person? So there's a lot of ways we can actually collaborate, but in that case we need to set up firewalls and everything, but we're thinking about it too, yeah.
One last question, and then maybe you can stay after the seminar so people can ask more. Yeah.
For a lot of medical questions, you need annotations actually.
Yeah.
These annotations are mostly done manually by experts.
Mm-hmm.
If you have so many data sets, how to make sure that these annotations are first of all done, and then also properly done by experts, not just random people think like, yeah, I think that's a cough or a admin attack or something like that.
That's a good question. I think you can do it. You can do different things. So either you can kind of crowdsource a problem, so you can make a website available where these annotations can be done in a crowdsourced way. In other cases, yeah, I think this kind of collaboration also helps here. We see something similar in plasma physics, where you have plasma coming and you need to annotate when something happens. But what you can do, from previous annotations, we can build machine learning models that kind of make automatic annotations, which are kind of a good first step, and then other people can make new annotations more quickly. Yeah.
Okay, thank you, Joachim.
Thank you.
One more big applause, please. And I think you have a lot of volunteers for your workshop. Okay, please have a seat, the people that